Thank you.
Hello.
So, hello Copenhagen. In this talk, we're gonna illustrate the evolution of Hadoop at Spotify. So, regardless of the reason why you're here, and maybe you're here because you have your own cluster, or maybe you want to build your new cluster, or maybe you just want to learn about Hadoop. Well, we hope that this talk will gonna be useful for you because we're gonna bring up real-world examples of incidents and issues and bugs that we had and how we tackled them at Spotify. But please keep in mind though that every single cluster is different, so what worked for us may not work for you. But we hope that next time you see a similar issue, you can take this knowledge and make more data-driven decisions about your issues. Before we dive into the details though, let's first introduce ourselves. So I'm Rafal and this is Josh. Josh is the product owner and I'm an engineer at Hadoop Squad. And we both kind of fall in love with Hadoop about 2 years ago when we moved to our beautiful Stockholm office and we started supporting this one of the biggest Hadoop clusters in Europe. And that was a huge responsibility but also great privilege. So now that you know who we are, let's take a look at the agenda of the talk. So first, we're going to talk about the issues, the pain points, how we were trying to keep our cluster up and running. Then we'll gain the focus, we'll stabilize the cluster, and then at the end, we'll finish it hard with the future and our current features of our infrastructure. So let's get started.
Sure. So to start off with, as Rafal mentioned, we're going to start talking about the beginning of big data at Spotify when we first started with Hadoop. But before we do that, we're just going to go back up a second and talk about what Spotify is. I realize it's probably pretty well known in Scandinavia, but just in case so we're all on the same page. Spotify is a music streaming service. Some people think of it as like iTunes on the cloud. It was launched in 2008. There's two main tiers, a free tier and a premium tier that costs around 10 euros a month. It gives full access to all our catalogs of songs. It's available in 58 countries. I just looked, and over 48 of those countries average stream over 1 million streams per day. Some other numbers, we have over 75 million monthly active users. Those users choose from a catalog of over 30 million songs, over 4 million artists, and they combine to play around 1 million streams every day. So that's a lot of data. And because it's a lot of data, we have a pretty massive data infrastructure to process over it. We just upgraded. We added another 300 or 400 nodes. We got up to around 1,700 nodes. We think we're probably the biggest Hadoop cluster in Europe. If you're not, we'd love to hear how big your Hadoop cluster is. We have 62 petabytes of storage. We get over 30 terabytes of logs every day incoming, generated by users. We run about 20,000 Hadoop jobs per day, and those jobs generate over 400 terabytes of data. So that's a lot of data, and you might be wondering what we do with all that data. Now let me ask a question real quick. Is there anybody in here that's a runner? Okay. Well, if you use Spotify, you're in luck. A few months ago, we released this new application, a new feature inside the application that's a running app. And what's really cool about this is it gives you a custom playlist based off your running tempo. We found that actually running with a beat, when you're in rhythm with your cadence, improves performance as much as 15%. And what's really great is that we combine your listening habits, your personal listening habits, and the characteristics of all the songs that you like to listen to. Things like the mood and the energy, along with the song's beat per minute to generate a bunch of different customized running playlists, familiar and interesting music at every beat per minute for all our active users. Another feature that we've recently launched that you might be familiar with if you're a Spotify user is called Discovery Weekly. It's 2 hours of personalized recommended music delivered every Monday for all of our 75 million monthly active users. And this has really been one of our most successful features that we've ever launched. Every Monday we get a flurry of new Twitter activities that say how great their playlist is this week and how much better it was from the past. Or if we're late with the data, we get a bunch of Twitter complaints about how their playlist isn't there yet. So we know that it's really important to our users. Behind the scenes, it's running a variety of different machine learning techniques that's all based off of extracted features from the data.
Yeah, these features are pretty cool, but before we dive into them, let's first take a look at a very simple one. So this is a top list for Denmark, top 50 songs that users are listening to in Denmark. So let's spend 2 seconds and think about how would you basically implement this feature. So if you think about it, the most simple, the most brute force solution will be probably to just like throw this data into database and then run a simple query like this one over here. So you select some track ID, some artist ID, you count it, you group by, you have a limit, you have, voila, you have your feature, right? Pretty simple. The problem is that as soon as you start getting this amount of data that Josh was talking about, remember 30 terabytes of data per day that we have to ingest, then that starts to be an issue, basically. So we knew right from the very beginning that we need something that will scale better with our scale with the amount of data that we're getting. And also, top list is just one type of report. We have to create lots of different reports, lots of different calculations that we have to do on the data. So we have to be flexible when it comes to the type of calculations we're doing. And the third reason, we're getting different data from different sources in a different structure, so we have to be flexible about the data and the structure of it. We basically needed something like Hadoop. And that's why we started playing with Hadoop in 2009. So very early in the life of Hadoop. And we had a couple of learnings about it at the very beginning. So basically now we know that it scales pretty well, and then it's flexible when it comes to what kind of frameworks you want to run on top of it. And also with the schema on read principle, it's actually flexible when it comes to what kind of data you want to store on it. But then there was also another cool findings, which is Hadoop streaming. And Hadoop streaming is a feature of Hadoop that allows you to implement MapReduce jobs in a language different than Java. And that was important for Spotify, because Spotify back then was a big Python shop. So that allows us to take this extensive knowledge of Python and put it on top of Hadoop. And then we started implementing this intensive pipelines using Python. And basically, we got a lot of insights and data, and that allows us to make data-driven decisions and make Spotify so successful the way it is today. But to be honest, I'm missing one important piece of the story. I'm saying that, yes, you can run these pipelines, and you can get these insights, and you can get lots of knowledge, but the first problem that you're probably going to get is how to move the data to Hadoop. So that sounds like a simple problem. Well, you just store it on HDFS, that's the simple solution, but, well, it's actually not that easy. So let's take a look at this problem from Spotify's perspective. So at Spotify, we have this notion of access points, which are machines that all the clients connect to. So every time you open your client and you want to request a playlist or anything like that, you want to get any backend service, you go through the access point. And every time you request something from the access point will log that on that specific machine in a tab-separated format. And because of that, that introduces a lot of a specific type of issues. So the first one is that data is pretty raw and dirty. So we have to make sure that our ETL pipelines are rock solid, and that we make sure that every single record is clean. And that actually is not so simple with tab-separated values. Another thing, if you have a tab-separated value, well, the schema evolution is not that simple, and it's specifically difficult at Spotify because we have lots of small teams, and if you want to change something in the structure, if you want to add a field or remove the field, well, you have to talk to lots of different teams. And it's not uncommon for a team to change something without talking to anyone, and then you learn about it only by having an incident downstream in the pipeline. So that's another issue. There's another set of issues that we're having because we have a Hadoop cluster in only one data center in London. We have to move all the data to one single place in London, and that introduces issues with networking and what happens if you have to duplicate the data, we have to deduplicate it later, so on and so on. So given the problem, we started, there's one more important issue also. So at Spotify, we treat our logs very carefully, and we have to make sure that we get all of them because we treat them like financial transactions, because we have to pay back to our artists and make sure that they are satisfied with Spotify. So logs are super important for us. So with that problem, we implemented our first iteration, which was LogArchiver. And that solution actually lasted very long. So that solution lasted from 2009 to 2013. And you will be surprised because it was very trivial. It was just a set of Python scripts that will basically compress the logs and then rsync or RCP files between machines all the way to data center in London. And that jobs will basically be croned, and basically it had a lot of issues. And what kind of issues? Well, because it was croned and because it was trivial and it was set of Python scripts, it would fail a lot. There was no proper monitoring, there was no proper alerting. So every time there was an issue, our engineers would have to go to a specific data center, SCP files manually, all the way to London and make sure that all the logs are there. If we had to scale our access points, we had to add more machines or we have to remove an access point, that would be another manual work for our engineers. So it was a huge, magnificent failure.
But before you bemoan it too much, I must also introduce an important part of Spotify's culture. And that's best summarized by 2 words: embrace failure. The idea is pretty simple. Basically, when you're failing, you're learning a lot. You're learning a lot more than if you're being very conservative and moving slow and being afraid to fail. So in the case of LogArchiver, we actually learned a lot. We learned a lot about what not to do with log delivery. For example, you don't make it rely on cron if you want to expand your nodes and scale up all around the world. The failures and learnings guided our next generation of log delivery, which we built on top of Kafka. Now, let me ask another question. Is anybody using Kafka in their production environments in this room? Is anybody familiar with it? Okay. So Kafka is basically a messaging queuing system that was open sourced by LinkedIn that has a publish-subscribe model, or Kafka's terms, producer-consumer. So we tried a few different messaging systems when we were evaluating the next generation of our log delivery. And we found pretty early on that Kafka just worked the best. We had latency go down from our access point, as Rafal mentioned, to our HDFS cluster go from hours down to seconds. And this opened up a wide variety of new use cases that we could do with the data. For example, real-time processing with Apache Storm. So this is a simple picture of what our architecture looks like. So we have the 30 terabytes of data that's generated from users connecting to our access points. That's passed alongside to site local groupers that consume all the events produced from the access point. They compress them, they encrypt them, they send it over the internet to London, where it gets consumed into our Hadoop cluster. So we'll be pretty honest, we've had a lot of problems with even this log delivery system. But that's related a lot to the Kafka system that we're using. We're using Kafka 0.7, which is a little bit older architecture. And it's also due to the fact that we have an end-to-end delivery system that we built on top of Kafka that really allows us to get the reliable delivery because these logs, as we said, are pretty important. But our log delivery system is constantly evolving at every new issue that we hit. And in fact, right now, we're in the process of evaluating a bunch of different log delivery systems so we can improve it and fix some of the bugs that exist in our system. So now that we have data inside of Hadoop, you might want to start doing data. You might want to start doing something with data. So you run a few jobs, and you might schedule them. For example, like in cron, like this. And run the jobs at predictable times. This might work initially, but what happens if your previous job fails? You don't want to process over incomplete data, because that's actually worse than not processing at all, because you'll have inconsistent results down your pipeline. So faced with this challenge, one of the early engineers at Spotify, his name was Eric Bernhardson, tackled it by creating a new tool. It was called Luigi, because it handles the plumbing of Hadoop jobs. And also because it's green and Spotify's green, and that's cool. So Luigi is a workflow orchestrator that's written in Python that allows you to define job dependencies programmatically. So if, for example, in the royalty calculation, your royalty calculation pipeline depends upstream on some ETL jobs, it's going to make sure that those dependencies are complete before it runs the royalty calculation jobs. If it's not complete, it's going to schedule them. So it's been a very successful project that was first open sourced by Spotify in 2011. It's used all over the world at hundreds of different companies. We're finding new ones each and every day, including some really big ones like Foursquare and Stripe. Unfortunately, we don't have so much time to go down into the details of Luigi, but if you're interested in this, we encourage you to go to the GitHub page down there and check it out.
So now that we have data on HDFS and we have a scheduler that we can schedule the job with, we started getting more and more engineers into crunching the data. And that was pretty cool. And what comes with engineers at Spotify, there's feedback. And there's a good piece, positive feedback, and there's also constructive negative feedback. And one of it was that there's no data catalog, so it's hard to find data sets on HDFS. And every now and then, an engineer would have to go to HDFS and list some directories, then maybe at the end it will cut it. So like in this case, looking for the boat on a data lake. Every single execution of this HDFS client would take a couple of seconds because it has to load a JVM, it has to load the libraries, and so on and so on. And that was a pain point for our engineers. And because we like to experiment, we've decided that we'll experiment with the RPC protocol in HDFS. And that's how another open source project at Spotify was born, and that was Snakebite. Snakebite was originally created by Wouter de Bie. And in the nutshell, it's basically a pure Python HDFS client, which means that everything happens inside Python. There's no Java happening in this client. And it's actually very simple and very intuitive when it comes to simple read operations on HDFS. And how fast is this? Let me show you on another slide. So here you can see 100 executions of vanilla HDFS client on top, and below you can see 100 executions of Snakebite client. And you can see that it's roughly 10 times faster than vanilla HDFS client, which is pretty cool. But what is also nice is that it will actually use less resources than vanilla HDFS client. It will use less memory and less CPU. And that is actually pretty handy, especially if you have a service that interacts with HDFS a lot. And at Spotify, we actually have such service, and it's Luigi. Because Luigi actually, to schedule the jobs, it has to do a lot of existency checks on HDFS. And when you start running tens of thousands of jobs, that can actually overload the machines that you run the scheduler on. And we actually had this issue. So we've decided that we will move from HDFS client to Snakebite client. And what we've noticed immediately afterwards is that our checks are more stable, are faster, and scheduling works more promptly, which is pretty cool. And I encourage you to take a look at the GitHub page and search for Snakebite.
So now that we had our Hadoop cluster up and running, and we have the Kafka that's loading data into Hadoop, and we have some tools like Luigi and Snakebite so that all developers around Spotify could access data and run Hadoop jobs, we started to run into a new issue. And that was that developers actually were running a lot of jobs. They were running more and more jobs, and the importance of those jobs were just increasing over time. And the problem was that the team that managed the Hadoop cluster was also the team that was writing jobs too. And they were also developing and supporting tools like Snakebite and Luigi. And they didn't have a lot of time for Hadoop maintenance. And if you're familiar with Hadoop, a Hadoop cluster without time for maintenance is an accident waiting to happen. And after a particularly hairy incident that caused multi-day outage, we decided we had to change something. And the decision was to form a team. So the team started with Rafal, myself, and another engineer at Spotify. And we had a very simple mission when we started. The first part was that we had to migrate to a new distribution of Hadoop that included Yarn. The second part, and the most important part, was that we had to make Hadoop reliable. And so you might be wondering how we did. So let me show you in this graph. So in the first section, this is when Hadoop was essentially ownerless at Spotify. We had a lot of random issues and outages that caused downtime. Around the company, Hadoop was kind of like a dirty word, because even though it was really easy to write and run jobs on the cluster, you weren't so sure if it was going to be up when you actually really needed the results. The second section is actually when we started the Hadoop team at Spotify. We addressed a lot of the low-hanging fruit and started to improve reliability right away. The third section is when we upgraded our Hadoop cluster to a distribution that included Yarn. So there were some complications involved in that. It was also complicated by changing distributions. In the first quarter of 2014, we added name node high availability. And that also introduced the problems of their own because of the scale of our cluster and the size. Just nothing's ever as easy as the Hadoop book says it is. So in the third section, this is when, or the fourth section, I guess, this is when we actually started to get pretty reliable and predictable. And we were actually we did this by making our Puppet configurations that we use to control the Hadoop cluster really rock solid. We added a lot of monitoring alerting so that before issues happen, we were aware of the fact and could prevent them. And we also built some infrastructure to make upgrades easier. So we're starting to be seen as a model team around Spotify because we were really improving the reliability and addressing our users' biggest problems.
That was all cool, except at the end, you can see the last bar, and this is the last quarter, and you can see a significant drop in availability of our Hadoop cluster, and that is mostly because of our process of scaling our Hadoop cluster from 1,200 to 1,700 nodes. And as Josh said, yes, we had Puppet, we had monitoring and alerting, and we could prevent something that we knew about. But as it turns out, there was another class of issues that we were starting to hit. There was a class of issues or basically bugs in Hadoop code. So the lesson is that when you scale Hadoop, you also scale the hidden bugs that come in the code. And in our case, they come, we can see them as soon as we start scaling over, let's say, 1,200 nodes. So in this case, you can see two specific issues that are super deadly to us, but in terms of small clusters, they wouldn't really be that deadly or they wouldn't cause downtime. In our cases, both of them basically brought the whole cluster down for more than 1 day. So let's take a look at the first issue, for example. So in the first issue, it's an issue with open files and failover. So when you failover from one name node to another one in a HA setup, the to be active name node will have to go through all the open files, make sure that they are still open and valid. That process was implemented in very poorly way. It was very inefficient way to implement that. And the whole description is in the code. In a small cluster, that wouldn't be an issue. In our case, where we have thousands of open, tens of thousands of open files at any given point, that basically brings the whole cluster down. What is funny is that that issue actually made us upgrade from one version to another, from 2.2 to 2.6. Actually, right after the upgrade, we ran into another issue, the second one, that actually also brought the whole cluster down. And it's also related to a failover. So remember, when you scale a Hadoop cluster, you also scale the hidden bugs in the code.
Yeah, so there were a lot of bugs that we ran into that were in the Hadoop code. There was also a lot of earlier challenges that we ran into just with our poor configuration and our needed to constantly adapt to change. But there were also some issues that we ran into that were totally 100% preventable, as I'll talk about right now. So a little bit over a year ago, the Hadoop team was doing a pretty good job, and we were pretty proud of the reliability of the Hadoop cluster and the success that we've had. And around the company, people were coming up to us and they were saying, "You're doing such a great job." So we thought we'd go celebrate, and we decided to go out to a bar in Stockholm and have a few beers and just celebrate our success. So when we were walking out to this bar, we all got a message coming in on our phones. We opened it up, and the title said something like this: "I think I made a mistake." Now, when we opened up the email, we realized that one of the users in New York had run a command on the cluster that looked something like this. Now, maybe someone can see what's wrong here. Maybe now. Maybe now. So when I realized the issue, I looked up and I saw Rafal's face, and it was like this: "Mother of God, what have they done?" So it turned out that the user in New York had accidentally put a space in the command that he was running in between his team's name and the folder that he actually wanted to delete. And he had wiped out his entire team's directory of data. This was over a petabyte of data that was collected over months and months of pretty intense Hadoop processing. So we were standing there on the sidewalk in sunny Stockholm, and we're trying to decide, what do we do? Should we go back to the office, shut down Hadoop, try to recover some of the blocks before they get permanently deleted, or do we just continue on to the bar and deal with it tomorrow and pretend we didn't see it? Fortunately, we didn't actually have to make that decision because another user from the same team of this guy in New York replied to the thread saying, "Don't worry about it, Ed. We can actually regenerate some of the most critical data in just a few days. You know, hooray, we just saved a lot of space on the Hadoop cluster. So from this, we learned a few really important lessons. The first one is from our colleague Wouter. He always says this, is sit on your hands before you type. You know, especially if you're skipping trash in HDFS, or you're using some kind of super user. You know, before you hit that enter key, make sure what you typed is actually what you want to run on the cluster. The second one is that users always want to retain their data. And as we found out in this specific case, you know, this team could regenerate all their critical data, and they really only needed a little portion of that 1 petabyte of data. And if we knew this beforehand, if we had actually challenged them a little bit harder, we could have saved a lot of money and space on a cluster and costs. The third one is that you should remove super users from your edge node. If you're familiar with super users, they basically have global access. They have super permissions on your Hadoop cluster. And at Spotify, we have this, you know, Swedish ideal of equality, and we have, which means that all engineers at the company have sudo access on the machines that they have access to. So if this user had used the super user and had that space a little bit earlier in the command, you know, me and Rafal might not be up here giving this talk today. So the fourth lesson we learned is that moving to trash is actually a client-side implementation in Hadoop. And in Snakebite, we hadn't quite implemented it. So we celebrated a little failure, we did a little hacking, and you can now safely remove from Snakebite.
That was a pretty cool incident and a funny one. But a few weeks afterwards, there was another one. So we had this external consultant over at Spotify, and his goal was basically to certify our cluster, which means that he would go through all the different parts of the cluster in configuration, and at the end say, this cluster is healthy or not, and this is what you have to improve. The first few days weren't actually pretty smooth, and we were kind of like happy about ourselves and proud because, you know, he didn't find anything, so we're like, yes, we're doing great. But on the day number 3, due to miscommunication and misconfiguration, one of the teammates killed our standby name node. And that was fine because it's a standby name node. Except then there was another miscommunication and we killed our active name node, which means that there was no master node in HDFS, which means there's no HDFS, which means there's no Hadoop. There's no processing. And that at our scales means around 2 hours of downtime. And that was specifically bad because there was this external consultant over, right? But that wasn't as nearly as bad as day number 4. So on day number 4, we're sitting in another room, there's this consultant, there's the team, and there's our managers, and we're talking about the incident and overall about the certification. And the consultant is saying something around the lines of, the fact that our testing and deployment procedures are like wild, wild west. And that was very difficult to listen to, but in the end, he was right. So, and we knew that. So right after the meeting, the whole team went to a room, and we've decided we're not going to leave the room until we come up with a plan to basically solve this issue. And we came up with something that may be actually pretty simple and obvious to you, which is a pre-production cluster. And pre-production cluster is made out of the same class of machines, exactly the same class of machines, very similar configuration, almost identical. And we created a set of smoke tests that we can run on that pre-production cluster, make sure that every part of that system is well integrated and works perfectly fine. And then we can use that, both smoke test and pre-production cluster, to deploy changes first to pre-production, then run the smoke test, get instant feedback, and then decide whether we want to actually deploy or not. That actually changed the way we test and deploy on production, which worked pretty well. Specifically, for example, for our recent upgrade, we're able to discover through 2 issues that would most probably cause a serious incident on the production if we have not discovered it before. While the Hadoop squad was trying to make the infrastructure stable, and was working on pre-production and all that kind of stuff, there was another effort ongoing in data, and that was to move from Python to JVM. So as we said before, Spotify was a big Python shop, and we implemented lots of pipelines in Python on top of Hadoop streaming. And over the time, we realized that that is an issue because we started seeing lots of failures of this kind of pipelines, because every time someone made a change in the Python code, it was very hard to test it, so people will basically throw it at the cluster, waste resources, just to get feedback whether they made a typo in a code or not. Or maybe there's a mismatch in the type because of the nature of Python. So that was one class of issue. Another one was that there was basically no testing infrastructure, so people would throw basically pipelines at the cluster, and also the performance was not there. So that is because of the nature and architecture of Hadoop streaming and also Python itself. So one of the engineers at Spotify, David Whitening, did an extensive overview of all the frameworks you can use on Hadoop, and you can find the links over here. And then afterwards, there was a discussion about all the frameworks, and we've decided that we will choose Apache Crunch as a supported framework for running MapReduce batch jobs at Spotify. And there was a couple of reasons behind it. I'm going to bring up 3 of them, which we think are the most important ones. So the first one is that you get real types, so you get type safety, which means you can get compile time errors. You don't have to throw the job at the cluster to verify that it's a proper job without typos or schema mismatch. Another one, you get a high-level API, which means that you can start thinking in terms of joins, group bys, call groups, on all kind of fancy functions instead of thinking in terms of this old map and reduce paradigm, which is very nice and makes the whole pipeline less verbose and easier to maintain over time by different engineers. Then the third reason is the performance itself that comes from JVM. And let's take a look at the graph over here. So on this graph, you can see the benchmark of Crunch and Hadoop streaming. And this is a benchmark for our production workloads. So this is not a synthetic one. These are our production workloads. And this specific graph is a map throughput in megabytes per second. On the left, you can see Crunch. On the right, you can see Hadoop streaming. And you can see that Apache Crunch is roughly 8 times faster on average, and almost 75% of all the Apache Crunch jobs are faster than all the Hadoop streaming jobs, which is a pretty good reason to move to JVM. And also, we were able to come up with a pretty neat testing environment for Apache Crunch on top of a mini cluster, which basically means now we can enforce our developers to create tests for their pipelines, which is also very nice.
Yeah, so that was a lot of evolution. So let's just quickly review what we talked about. So at the beginning, we discussed the difficulties of even getting data to our HDFS cluster and how we solved that using Kafka. Then we talked about some of the challenges that we had when we were first starting out and writing Hadoop jobs and using cron as the scheduler, and how we fixed those by using tools like Luigi and Snakebite. Then we talked about some of the issues that we had early on with availability and how we solved that, creating a team that was really focused on the Hadoop infrastructure only, and also how we improved the reliability by doing things like proper monitoring and alerting. Then Rafal recently talked about how we started to really focus on performance and improve by moving things from Python and Hadoop streaming to Apache Crunch. And this last section, we're going to talk about the future. You know, what we're working on now, what we're planning to focus on the next 6 to 12 months at Hadoop at Spotify. So this is a graph of the growth of Hadoop versus Spotify end users since 2012, when Spotify had just crossed over 10 million users. So since that time, Spotify's grown 650%, which is pretty great growth. But the user growth doesn't compare at all to Hadoop usage growth, the growth in demand for compute resources at Spotify. So which has grown over 4,000%, as you might see. So what caused so much growth? Now we attribute it to 3 main things. The first one is pretty obvious. With increased Spotify end users, you're going to have a lot more data. All those users are listening to a lot more song, which means that all the pipelines that you used to have, things like the royalty pipelines and the top charts, have to process over a lot more data, and they need a lot more compute resources to do that. The second one is increased use cases. So when we started out with Hadoop at Spotify, we used it for just analytics and our reporting pipelines. We didn't use it for a ton of things. These days, we use it to power features. Things like the Discovery Weekly is all, at the end, driven by Hadoop and all these massive machine learning and graph processing jobs. And we've really seen that just all the different use cases means you're going to be running a lot more jobs, and you're going to need a lot more processing power. The last one is actually really interesting. So we've increased a lot of engineers at Spotify that process over data. And that's driven growth a lot. In 2014, Spotify acquired this company called The Econist that's based in Boston, the US. They're a music company that's just obsessed with music intelligence. And before they came to Spotify, they actually never used Hadoop. But when they started and had access to a treasure trove of user data, they became hooked. And now they're some of our heaviest users and run some of the most massive jobs. Now we learned through all this growth what we learned through this growth is an important realization. That's that scaling machines is actually kind of easy. You know, we have alerts, we have monitoring, proper monitoring, we have really solid Puppet configuration that allows us to add new machines. You know, it's allowed us to go from 120 machines a little bit over 2 years ago to the 1,700, almost 1,700 machines that we have today without much trouble. Now we have run into some issues, as Rafal mentioned, with the recent adding of 400 nodes and or 500 going from 1,200 to 1,700. But for the most part, it's been pretty smooth. But scaling people, that's actually really hard. Now we're still a relatively small team at Spotify, but we support hundreds of users that are processing data. And they have different levels of expertise, down from the beginner to the expert. And we have trouble keeping up with all their problems. So you might wonder what we're planning on doing about that. We're starting to automate feedback. We want to provide information about Hadoop jobs to users immediately after job completion. Things like, did your job fail with a specific error? Maybe we know about that error, can link to the Jira ticket, and maybe the workaround for it. Maybe your job is launching with the incorrect user permissions. So we'll try to put up a warning sign before you run your job so you don't waste all the compute resources only to come up with nothing. But while we're working on this, we've deployed a few things that are already helping us and might help you too if you're running Hadoop. The first is a project called Inviso. This was written and released by Netflix a little bit over around a year ago. Inviso allows you to see what's going on with the cluster in real time and provides some really nice visualizations that make it obvious. For example, if a single job is dominating the cluster and using all the resources. It also contains some pretty cool visualization tools that you can go down in the individual job level and see how the life of the job and how it's performing. And you can use that to improve job performance. I'd really encourage you to check it out. Sorry. The other thing we've been doing seems so obvious that we've been really surprised at how effective it's been. So every quarter, we publish a newsletter that contains all kinds of different information and statistics about Hadoop jobs. Things like the growth of Hadoop compute demand, the increase of storage, the top failing jobs of the cluster in that quarter or in the month, or plain old Hadoop reliability. Now, we always get really great feedback around this newsletter. Sorry, I'm getting all cold. But a few months ago, it was even more effective because it identified a single job that was running every day and wasting over 10% of the cluster's resources because it was always failing. Now, before we published the newsletter, the user that owned this job didn't even realize his job was running every day on the cluster and failing. But when he saw his name on the newsletter, the social peer pressure alone caused him to immediately go unschedule his job and vow to us that he'd never launch a job on the Hadoop cluster without properly testing it and without kind of certifying with us. So just from the social peer pressure, it improved user performance, which was great for us because we didn't have to go in and manually tell him that he has to stop doing that stuff, which was great.
Since this is a data talk, we have to mention Spark. So there's Spark slide. So yeah, we are evaluating Spark, and we've been playing with it since the very beginning. We had some issues with it, and pretty recently we started to experiment with Apache Zeppelin on top of Apache Spark. So you've probably heard about Spark, but how many of you have heard about Zeppelin? Cool, so there's a couple of people, great. So you can think of Zeppelin as the IPython on steroids on top of Spark, right? So what it gives you is that you can basically dive into data, slice and dice it a little bit, and get the result in a nice visual way, right? So it's like a notebook experience on top of your Spark. And The way we want to use it is we want to use it as a glue tool where you can connect to all the different pieces of our infrastructure, fetch the data in, quickly process it, get a nice visual result, and then the engineer can decide whether there's value in that data and whether there's a need to deploy a proper production-ready pipeline on top of Scalding or Crunch or anything like that. So that's where we see it. We have some good results from the very beginning. I encourage you strongly to take a look at Apache Zeppelin. This actually brings us to almost the end, which is 2 takeaways. So this is kind of the most important slide of the talk. So 2 takeaways. One is that there's no golden path, especially when it comes to big data. There are no patterns. There are kind of emerging patterns, but the engineers are kind of defining it or up to define it. So when you have a problem, when you have to design a system that will deal with data, we would encourage you to take a look at the problem and try to implement it in the most simple solution that you can come up with. So try to avoid premature optimization as much as possible. If it's an anti-pattern generally, then in big data, this is like the root of all evil. And then the second takeaway is that evolution is an ongoing process. So whatever you're going to plan to design or implement has to be designed in a way that makes it easy to iterate over it. So basically, you create something, then you will have to most likely just throw it away very shortly right after and implement something on top of it. And you have to implement it in a way that makes it easy to swap it, basically. So these are 2 kind of simple takeaways, kind of generic a little bit too. But if you kind of live up to them, that will make your life much easier as a Hadoop administrator or data engineer. And that brings us to the last slide, which is we are hiring, and we need engineers in New York, Stockholm. So if you want to join, you can talk to us afterwards, or you can write to us on Twitter. That's the end.
All right, thank you very much. I think we have time for questions.
All right, thanks, guys. So, who wants to start? This one, because you happen to be close.
Hi. How do you deal with schema changes? You mentioned it. That is a problem with the format.
How do we do with schema changes? The question is, how do we deal with schema changes? So most of it is actually implemented as a schema repository right now, where we have a project called log parser, which basically defines what are the fields. And then every time you make a change, you can change that in that log parser, but you have to make sure that everyone knows about that change and all the pipelines that are downstream are up to date with that change. That doesn't really work all the time. And in the most recent architecture, we're working on a more centralized schema repository where you would fetch the schema from that repository, and that would basically be dependent on the data that you fetch. So let's say that you want to process something that is from 2 years ago, then the schema will be there in that repository that you can fetch, but it's not in there. It's not there yet.
And I can't remember if we mentioned, but we do use Apache Avro, so that helps out a lot.
Okay, there's one over here.
You mentioned that the cluster was not stable in the beginning. What was the reason for that?
Before the Hadoop team was started?
Yeah.
Yeah, so we had a bunch of different issues. A lot of them were really low-hanging fruit. Like nobody was managing the data growth. So every once in a while, we'd be expanding the cluster when you run out of disk space. And there was really it was always reactive. That was the problem. So we'd run into 90% disk utilization, which is kind of the danger zone, because it means that individual disks are 100% full, or you'll have individual nodes that are 100% full when it hasn't properly balanced. And that'll cause a bunch of job failures, and eventually it'll just run into all kinds of crazy edge cases in Hadoop. So that was one of the big reasons. There were also some other really interesting issues that we ran into. I'd have to go back and look. But some bugs, some misconfigurations, because Hadoop is not the best documented code. There was even some configuration parameters where It said this parameter is milliseconds, but it actually turned out to be seconds, and that like really, I remember that was one massive issue. Yeah, so there was also all sorts of little small things.
It was kind of like a small, like Josh is saying, kind of small stuff. Like there was no alerting. So for example, we would run out of space on the disk drives on name nodes. Would be like, name node will die, and then Puppet was not running. So every time there was a change, for example, in network, that was kind of serious, and it would not be propagated, deployed on name node. All of a sudden, no one can connect to name node, which is also a problem. Or like disks would fail, like we would not have a write setup on name nodes. That's another problem. So kind of simple stuff that you can do, kind of long hanging fruits.
Yeah. Actually, there were alerts. There were just way too many alerts, and they were totally useless. I remember when I first started at Spotify, you get your email starts like a few weeks before you actually your first day, and I had like over 10,000 emails, and like all of them were, standby name node disk is full, or just we had the over alerting problem. So many alerts that it's absolutely useless, and they weren't very specific like we made later.
Yeah, there was a deadlock in data nodes too, and I remember that we've made a change in the time that it takes for name node to mark the data node as dead. And the other one was I think the milliseconds and seconds. So in the way we wanted to make it longer, but we've made it shorter, which made the whole thing worse.
Yeah.
What else was there? But there were some bugs, there were some misconfigurations, there were low-hanging fruits.
Okay, some more questions? All right.
How big is your pre-production cluster?
Right now it's 12 nodes,
Yeah.
and two.
We expanded it to, I think, around 40 nodes now.
Okay, thanks
Yeah.
for your nodes.
So we recently, it was 12 nodes for a long time, but then we recently had to upgrade about, it was a month and a half ago, or even a month ago. So we had to bump up capacity because we were 12 nodes and 1,300, 1,700 nodes. It was hard to actually move data there to do pre-production tests. So we had to bump up capacity, I think, to around 30 or 40 nodes. But it's pretty elastic. We might have gone back down to 12. I don't know.
Okay, more questions for the guys running the biggest Hadoop cluster in Europe. You guys are just gonna be kicking yourselves when you get home, and you realize that question you wanted to ask. All right, everyone's like, oh, it's time, it's
There's
time
one
now.
over there. So the question is whether we use physical nodes or virtual one. So we have physical cluster in London. Yeah.
Yep. We actually had a slide of the specs, but we decided to remove it. Yeah, but we run Dell servers, 1,700. We have, I think, 3 different generations of servers. Our oldest ones are about 3 or 4 years. Our newest ones we got, I don't know, 3 months ago delivered. They're pretty beefy. They run, we have 12 disks per machine, 4 terabytes a disk. Yeah, about 24 cores.
Yeah, depends.
machine.
Yeah.
Okay, more questions?
About backups. Yeah, so it's kind of a funny story. So LogArchiver we talked about before actually did our backups too. So it would write to HDFS. It would also write to Amazon. I think it was S3, so that if we needed to restore, we could just reprocess the data from raw. If we ever actually had to do it, though, it would be a different story because actually getting the data from S3 and reprocessing it with old formats and stuff would be a nightmare. Yeah, so when we killed it, we had to come up with a new solution. So what we do now is we don't copy our raw data because we save like the recent history inside Kafka. There's some mechanisms inside Kafka that allow you to persist data for a certain period of time. So all of our core data sets, we make backups of. We encrypt them and we copy them to the cloud. So now if we want to restore them, hopefully it'll be a lot easier. We can find out what's been deleted, just copy that data set and reprocess from there instead of going all the way back to the raw logs.
We also use snapshots.
Yes, that's right.
Which also is another, like, there's a cool feature of snapshots, which basically means that you cannot really delete snapshots easily, which basically prevents you from deleting everything. At least you will get, warning, error that, you cannot delete everything because there's a snapshot there. So that's also like a cool feature of snapshots. But we use snapshots too.
Yeah. Funny little story about snapshots. We're at Agile Shop. We do kind of Scrumish style. And we had a sprint demo with a lot of our stakeholders in the room, and we were talking about how we did snapshots and how it would make it harder for a user to accidentally delete his entire team's directory. So we'd implement this feature, and we had tested it out in our pre-production environment. It worked fine. We decided that in our demo, we were going to launch it on the production environment. But we didn't have to talk about was actually, should we test it on a production environment too? So one of our engineers kind of went a little rogue, Guido, and he decided, I've read about it. It's going to work. So he's right there in front of everybody. He's like, okay, delete root. And there was about a second or two. We were sitting there like, oh no, what's going to happen? And luckily it said, you can't do this because of snapshots. So it was a successful demo, but probably a little bit unnecessary. We could have done that on a pre-production just as easy.
I think we're glad that you didn't have to learn from failure there, because then we wouldn't get to hear you today. So,
Yeah.
All right, everyone, thank you. Please remember to submit a rating, and also remember if you have other questions or feedback to give these guys, you can put it in the app and it will get to them. All right?
Thank you.
Thanks, everyone.